Welcome to Geometry. It's chapter 14, lesson 1. We're beginning a new chapter on regular polygons. Remember to subscribe, smash the like button, leave a comment, and a nice one, please. Okay, lesson 1, regular polygons. What makes a polygon regular? What does the word regular mean?
Equilateral.
Yes, and yes. Equilateral and equiangular. That's what makes a polygon regular. All right, so let's look at the different types of regular polygons on the top of page 573. The smallest polygon is a three-sided polygon we call a triangle. It is equilateral. What is the measure of every angle in an equilateral triangle? 60 degrees. 180 divided by 3. The next equilateral polygon is a square. What's the measure of every angle in a square? 90. The next one is a pentagon. It's 5 sides. How do we get the measure of every angle in a regular pentagon? It's not 360, it's 360 plus another 180 divided by 5. Every time we add a side, we're adding another 180. So it's 360 plus 180 divided by 5. What is that, Blythe?
It is 108.
Each angle is 108. The next one is a regular hexagon. We are going to focus a lot on a regular hexagon. So let your little radar antenna go up, because a regular hexagon is going to be different from every other one. It is a special case. All right? And to get the measure of an angle there, you then add another 180 and divide by 6. And then the next one is a 7-sided heptagon, which we won't deal a whole lot with. The next one is a regular octagon, and I always think of stop signs. That's an 8-sided. A 9, is that 9? Nonagon?
Mm-hmm.
And what's decagon?
10.
10. What's dodecagon? 12, that's right. What if it has 34 sides?
34 gone.
34 gone, right? If it doesn't have a special name, you're just going to list the number of sides and put the word gone. G-O-N. Every regular polygon is cyclic. All right, y'all remember what cyclic means? What does cyclic mean?
Each one of its vertices are on a circle.
Inscribed
on
in a circle, right? That means there's a circle that can be circumscribed about the polygon such that every vertex would lie as an inscribed angle on the circle. So every regular polygon has a circumcircle that can be circumscribed about it. So we'll just use the hexagon initially. All right, just pretend. I know it doesn't look very equilateral to me, but pretend that's a regular hexagon. If a circle were circumscribed about it, then that would be called a what?
Radius.
A radius to the circle, right? That's a radius. And if I drew 2 radii, they're not going to look equal, but just we're pretending, right? Then I would make a triangle, right? And that's correct. So I would be bisecting 2 inscribed angles right? This would be an inscribed angle. All of these are equal. So what does that say about all the arcs? Equal chords have equal arcs. So I could find the measure of each arc. I can find the measure of each inscribed angle. And so let's do that. Could I know this angle? That angle theta.
Yeah.
It intercepts, let me just label the sides. A, B, C, D, E, F. So if I want theta, what arc does it intercept? What arc?
FBD.
FBD. And I can figure out the measure of that arc, right? So help me figure out the measure of FA. How would I figure out the measure of FA? Equal arcs, equal chords have equal arcs. All the way around is how many degrees? 360 all the way around. How many equal arcs do we have?
6.
1, 2, 3, 4, 5, 6. So if I divided that by 6, I could get the measure of each arc, which is 60 degrees. So that's 60 degrees. That's 60 degrees. That's 60 degrees. 60, 60, and 60. So I could look, what is the measure of arc FBD? FBD. How many 60s are there? 4. Did you say 4? So 4 times 60 is 240. And the measure of an inscribed angle is half the measure of the intercepted arc. So that angle is 120. This angle is 120 degrees. So when I bisect, okay, well, let's not even talk about that yet. Okay, that's 120, all right? Could I figure out this angle? What kind of angle is this?
Central.
That's a central angle. And a central angle, how does it relate to its intercepted arc?
It's equal.
It's equal. So what's angle X? 60, all right? All right. All radii are equal, right? So this triangle is at least an isosceles triangle. Would you agree? Because all radii are equal, even though mine don't look equal, but they are. Because it's regular. My drawing is not regular, okay? So what do these two angles have to be?
60 degrees plus 120 is my 60.
Correct. 120 has to be the sum of them, but because angles opposite equal side have to be equal, you take the 120 and divide it by 2, so you get 60 degrees. So what kind of triangles do the radii make inside of a hexagon?
Equilateral.
Equilateral triangles. That only happens in a hexagon. Such that the radius equals the length of one of the sides of the hexagon, or of the side of the hexagon. That is only happens with the hexagon, all right? Now let's suppose we're going to come back to that, but let's suppose, I'm moving y'all over a little bit. Let's suppose we have a pentagon. A regular pentagon. All right, so back here. When we draw a radii to the vertex, what did it do to that whole angle? It bisected it. All right, so let's remember that. All right, so what would that angle be? How many?
72.
72. What is that? 360 and 180. What's 360 and 180? What's 360 and 180? 540. Nope.
Yeah.
540. Thank you. Divided by 5 is
108.
108. All right. So that's 108 degrees. Got it? Because all the way around has to be 360. And this central angle has to equal the measure of that arc if we circumscribed a circle about it. We're not circumscribing a circle about it. That can't be right, huh? It's got to be 360 divided by 5.
72.
72. What did I say before? It's 360 divided by 5. I was looking at this angle. This angle is 108. No, it's got to be 72 times. This is 108. Right? No. That would intercept this arc. What's 72 times 3?
216.
So the arc would be 216, and half of that is 108. Okay, so 108 is correct. So here's the 108. All of these angles are 108. 108. But if I'm looking here, each one of these is 100. What's 360 divided by 372? 72. Each arc from each vertex is 72, so that's the measure of the central angle. All right, so then can I figure out what those are, what those angles are? Again, we have, since these are both radii, we have an isosceles triangle. So you take 180 minus 72, which is 108, and divide it by 2, which is what? What's 108 divided by 2? 54. So these are 54 degrees. All right, now I'm going to pull this triangle out. All right, so that's a radii, that's a radii, that's the length of a side. And if this is 72, if I draw what we've known at this point as an altitude, because it is an isosceles right triangle, or an isosceles triangle, then it would bisect that angle. So what's half of 72? Half of 72. 36? Is it 36? 36 degrees. And this would still be 54 degrees. All right, we've known that thus far as an altitude when we're talking about a triangle. But now we're going to have a new word. All right? It's going to be called, when it's inside a regular polygon, from the center perpendicular to a side. So it's from the center perpendicular to, and actually it's going to be the midpoint, to the midpoint of a side. The name of that is an apothem, an apothem, most people call it. It looks like apothem, but it's pronounced apothem. And we can use trig to solve for a radius or the apothem, the length of an apothem. All right? So because it goes to the midpoint, the length of this side would be the half of the side length. Make sense? And to get the 36, we began by taking 360 divided by the number of sides. So we took 360 divided by the number of sides, which was 5. That's how we got the 72. Then to get the 36, we took half of it. Got it? That's how we got the 36 degrees. Such that that would be 360 over 2n. If I simplified that, it would be 180 over n. So if we took 180 divided by 5, do you get 36? Do that in your calculators. 180 divided by 5. You get 36? Okay, so we can find the angle between the apothem and the radius by doing 180 over n, the number of sides. So if you do 180 divided by 6, what should you get? Half of 60, which is 30. Got it? All right, so you're following me so far. Got it? So in this pentagon, I'm going to redraw this over here. I'm going to make it bigger. That's the radius. That's half of the side. That's now the apothem. This angle here is going to be 180 divided by n. Got it? You following me? Okay. So I could use trigonometry to solve for the radius, or could I say just using, I don't want to use the apothem yet. I just want to use the side over 2 and the radius. So I'm not going to use the apothem. I'm just going to use the half of the side and the radius. Because the sine of that angle equals opposite over hypotenuse. Remember? Mm-hmm. All right, so I could write an equation. Okay, I'm going to erase this. Are we good to erase this? I could write an equation for the sine, and I could say that the sine of that 180 over n equals half of the side times the radius. Now, if I wanted to solve for the radius, I could. I would multiply by the reciprocal, which would be 2 over the side, 2 over the length of the side, such that the radius is equal to 2 times the sine of 180 over n all over the length of the side. Wait, I didn't write this as a ratio. Wait, back up. that it's opposite over. I'm like, I did something wrong. Opposite over hypotenuse. It's opposite over hypotenuse. Okay, now I did times. I'm like, that wasn't right. Okay, are we back here? Okay, now, how, do you remember how we solved when I want R equals? Ah, this is a nice one. I want R equals. Do you remember how I said you could swap your extremes? That's what I'm going to do. So R equals the side over 2 all over the sine of 180 over that number. All right? Now what if I don't want, this is called a complex fraction. So how do I move that 2 to the denominator? This is algebra, the rules of algebra. If I just want to affect this one fraction, I can only multiply by the value that equals 1. So can I multiply by 2 over 2? Yes, because what's 2 over 2 equal to? 1. And that eliminates the 2 there. You with me, Aaron? So that the radius equals the length of the side over 2 times the sine of 180 over n. So we could, this is not in your textbook. We could solve for the radius by taking the length of the side divided by 2 times the sine of 180 over n. This is going to be an important concept in the next lesson. Now, could I solve for the apothem using the same thing? I could. Now, if I want to solve for the apothem by using the side, half of the side and the apothem, what trig ratio would I use? If I want to solve for the apothem using that angle, side over 2, and the apothem, what trig ratio would that be?
Cosine.
Okay, that angle.
Yeah, tangent.
Tangent. It's the tangent. All right, I'm just going to have to erase. Here's some. All right, so now I have the tan of 180 over n equals the opposite over the adjacent. Again, I'm going to swap my extremes so that A equals the side over 2 over the tan of 180 over n. Like we did here, I'm going to move the 2 to the denominator such that the apothem is the length of a side divided by 2 times the tangent of 180 over n, and that would be an equation for the apothem. Length of the side over 2 times the tan of 180 over 2 over n, the number of sides. This really gives us, we could actually use this to solve for, we can use it to solve for the perimeter, but we're not going to do that. The area can be used by the perimeter, but this is the apothem. That's the two important ones, the apothem and the radius. So for the radius, we use the sine. For the apothem, we use the tangent. All right?